Hello and welcome back to the second half of Chapter 7. We're going to start today with Section 7.3. And we're still talking about confidence interval and sample size. And in Section 3, we're specifically going to talk about confidence intervals for the mean when the sigma is unknown. So we're still talking about the mean, but now our sigma is unknown. Or as I like to clarify it, I like to say that we only know the S, or the sample standard deviation. Okay, so we won't know the sigma, we'll only know the S, and that's going to change how we find our value. We will not have a Z value, a Z sub alpha over 2. We'll have a little bit different value. We'll get it off the same chart, we'll use it in a fairly similar way, but it is a different type of variable. So before we get into the actual problems, I want to put this slide up. I think I mentioned when I put it up the first time, but I'm going to put this up a bunch of times and to keep reminding of the process that needs to be gone through when you're making a decision on what type of confidence interval that you're working with. Okay, so your first question when you're looking at a confidence interval is, are you doing a confidence interval for the mean, or are you doing a confidence interval for the proportion? So in this case, we haven't done any on proportion yet, but in this case, before, in section 7.2, we had the mean, but we knew the sigma. And if the sigma is known, then you're going to use Z. So we talked about that this was in section 7.2. That's what we learned in section 7.2. This section, we're only going to know the S. We're only going to know S. And so instead of using Z in section 7.3, we're going to use what's known as T. And I had a student that kind of came up with this, and I thought it was rather clever. They said, I always remember that if you have an S, then you're going to use T, just like T follows S in the alphabet. So T comes after S. If you have an S, then you use T, because S-T-U-V, like in the alphabet. I thought that was rather clever. So, and we'll learn in this section what it means by use T. Again, it's just looking at the chart a little bit differently, getting a number a little bit different way. Now, then when we get back to, or when we get to section 7.4, we're going to be doing proportion, and we'll be back to using the Z. Okay, so when we do section 7.4, we'll be doing proportion, and we'll go back to using the Z in the table. But for this section, we're doing this route. We're going to be doing a mean, but we're only going to know the S, and so we're going to use the T. All right, so let's look at the T distribution. So the population standard deviation, when you're working with data in real life, when a researcher is working with data in real life, you typically don't know the population standard deviation. That's a big piece of information. And the only way that a researcher really knows the population standard deviation is if the population that they're studying and the thing that they're studying about that population has been studied a lot. So if it's been studied a lot and you have lots of samples, then eventually they can come to a pretty good conclusion for what they think the population standard deviation is. But that's not typical. Most research is new, or at least not as comprehensive as you would need to get the population standard deviation. So anyway, long story short, most of the time when a researcher is looking at data, they're going to be looking at and using what's known as the sample standard deviation, or the S, rather than the sigma. So remember, you have your population standard deviation, and that is your sigma, but we're only going to have the sample standard deviation, which is the S. Population always gets the Greek letter, and the sample always gets the regular alphabet letter. Not always, but almost always. So because we don't have the population standard deviation, we can't use the Z distribution, because that's all based on having the population standard deviation. And so what we're going to use instead is called students' T distribution, which is kind of a funny name. Why is it called students? Is it just because it's just for statistics students? And no, it's not. The reason that it's called student is kind of an interesting story. It was developed by a man named William Seeley Gossett in 1908, and he actually worked for the Guinness Brewery. He published his findings, his statistical mathematical findings, under a pseudonym, and he just picked student as his pseudonym. And it was to avoid revealing information about Guinness's research practices. They were like proprietary practices, and he didn't want to, get in trouble at work. So it was published under this pseudonym, student, and it just stuck. Ever since it's been called. I mean, it eventually came out that obviously that he was the one that developed it, but by then it was already being called the T distribution, the students' T distribution, and that stuck. It never got changed to Gossett's distribution or anything like that. And it was a real breakthrough because it helped, or it made it possible to analyze very small samples with unknown population variance, so unknown sigma. Okay, so if you didn't know the sigma and or you had a small sample, you could use this method and still get your confidence intervals. So it was quite a breakthrough as far as statistics goes. So what is the T distribution? Well, the T distribution is similar to the normal distribution, but it has a couple differences. The variance of the T distribution is larger. So you'll notice here these two dotted, this dotted line and this dotted line here, they kind of stretch out further than the black line, which is the normal distribution. And that's because they have a wider or bigger variance, bigger standard deviation. So it's a little bit more spread out. Because it's more spread out, it brings the peaks down a little bit. So you'll notice the peaks of the dotted lines are lower than the peak of the Z curve. And there is no single T distribution. The T distribution is adjusted based on the sample size. So the larger the sample size, you notice here we have degrees of freedom 20, that's related to the sample size. That's closer to that curve, that dotted curve that indicates that it's for DF equals 20, is closer to the black Z curve. And then the one that has DF equals 5, that indicates that we have a smaller sample, and that one's further away. It's flatter and has it even more spread out standard normal distribution. I'm sorry, larger standard deviation. But as that sample size increases, the T distribution does get closer and closer and closer to being the same as the Z curve, as the standard normal distribution. So how do we use it? Well, when we're using the T distribution, we utilize something called the degrees of freedom. And we're not going to go into a lot about what degrees of freedom are, but in simplest terms, degrees of freedom represent the number of independent pieces of information available that are free to vary in a sample to estimate the population mean. Again, we're not going to go into that in too much detail. Don't stress about it. We'll learn how to find the degrees of freedom, but you don't have to worry so much about what it means. So in practice, degrees of freedom adjust for the sample size. So smaller sample sizes have smaller degrees of freedom, and the t-value is farther from the z-value. So a small sample, you're going to get your t-value, and if you compared that to the z-value, it would be quite a bit different. But if you have large samples, so smaller samples, you're going to be further from the z-value. But if you have a larger sample, a better sample, because remember bigger samples are typically better, then you're going to get closer to the z-value. And if we have a sample size of n, our degrees of freedom is simply n minus 1. So degrees of freedom, you just take whatever the sample size is and you subtract 1 from it. And we're going to utilize that in our computation to find our t. So we're going to have a t value, a t sub alpha over 2, rather than a z sub alpha over 2. Other than that, our process is nearly identical to what we did in 7.2. So we're going to do one practice of just how to find that t value from the table. So the table that we used in the last section is the same one we're going to get. You notice now, you might not have noticed when we were doing it, but the name of this table is the t distribution. It does list the z values all the way at the bottom, but this is actually the t distribution table. So let's say we wanted to do a 95% confidence interval. So they told us in the problem that we want to do a 95% confidence interval. And we had a sample size of n equals 22. And we did not have, this kind of goes without saying, but I'll say it anyway, we don't have sigma. We only have S. Okay, so say that was the circumstances. How would we find our t-value? Well, you don't go all the way to the bottom of the chart, but other than that, it's fairly similar. So our degrees of freedom are found in this column right here, this first column. So in this case, our degrees of freedom are 22 minus 1, because remember, it's just the size of the sample minus 1. So our degrees of freedom is 21. And then we have 95% confidence. So you're going to start with your 95 here, 95%. You're going to come down until it corresponds with the row that has the 21. So your column is 95%, your row is 21, and this is the value that you would use. So instead of going all the way down to the bottom and getting that z value, you're going to stop here, and you're going to have a t sub alpha over 2 that's equal to 2.080. Okay, I'm going to pop up in the actual chart again, just so you know that little picture is kind of small. So if we were on this chart, not that chart, I'm one too far, just a second. Okay, so we're on this chart with the t distribution. Again, in this case, we had degrees of freedom of 21. And so you're going to start at 21. You're going to follow that over. And then we were at 95%. Hold on, I got carried away, went a little too far. And we were at 95%, which is this column. And we're going to bring that down until they intersect at the t sub alpha over 2. And literally everything else we do is going to remain the same. We're still going to have the same formula almost, except it's going to change the s's, the sigmas to s's and the z's to t's, but almost identical formula, and the process is almost identical. This is the only difference, is that you have to find your t value by stopping at the correct number of degrees of freedom. So let's see one in practice. Well, first the formula. So as we mentioned, as I just mentioned, the formula is the same. The only thing that's different is you'll notice that instead of a z, we call it t sub alpha over 2, and instead of having a sigma, we have an s. But we still have your x bar. You're still going to subtract this this part right here altogether as the margin of error, and then you have your mean in the middle, and then that's going to be less than the exact same thing on the other side, but you add the margin of error. And we do need still that we have a random sample, and we need that we have a sample size of at least 30, Or if the sample size is not at least 30, we can still use this if the population is approximately normally distributed. And what we're going to do for our case, our practices, since we're just trying to practice this right now, we're just going to assume that these both hold true for our examples. That either we're going to have a sample that's over 30, and if it's not over 30, we can assume it's approximately normally distributed. So we can assume that what the data that we're dealing with is okay to use these techniques with. So let's see what they sound like. So we're looking at this problem, and it says a random sample of the life expectancy of 9 Galapagos turtles. Okay, so what's our 9? That's our n, that's our sample size. We're found to have a sample mean of 122.9. That's going to be our x bar. Let's write these off to the side. So n equals 9. X bar is 122.9. And then it says a sample standard deviation of 34.2. Now that's not a sigma. A sigma would be a population standard deviation. So because it says sample standard deviation, that's the word that you're looking for, sample standard deviation, that's an S, 34.2. So our S is 34.2. Now we want to find a 95% confidence interval for the mean life expectancy of a Galapagos turtle or tortoise. So let's go back to our flowchart. So we had on our problem, it said that we were doing the mean for the turtles. So when we ask our first question is it a confidence interval for a mean or for a proportion? Well, it's for a mean, so we're going to go this direction. Okay. Is the sigma known or only the S? Well, in this case, we only know the S because they only gave us the sample standard deviation. And so we're going to follow this route, and then that's going to tell us use T. And whenever we use T, we're going to use that degrees of freedom. So T means we're going to be using the degrees of freedom. All right, so let's continue this. So we had our N of 9, our X bar, which is our sample mean of 122.9, our S of 34.2. So we have everything we need to fill into this formula. We have the X bar, we have the S, we have the N. The only thing we need is our T. Now it is shown on this little chart here, but I'm going to go to the bigger one so we can see it better. And remember, we're doing a 95% confidence interval. So let's get everything we need for the chart before we go to the chart. We know it's 95%, and we know that the degrees of freedom are N, which is 9, minus 1, which is 8. So our degrees of freedom is 8, and our confidence level is 95%. So those are the two columns, that's the column in the row that we're going to look for in our chart. So we have 95% again, so we're going to come down from this, in this column, and we had degrees of freedom, not 9, that was a sample size, 1 less than the sample size, which is 8. So we're going to come over from 8 and down from 95%, and we find 2.306. Now that's a pretty small sample size. And so you would expect that to be pretty far away from the Z, and it is. The Z was 1.96. And we have to change it to 2.306 to adjust for the fact that we don't know the population standard deviation, and we have a pretty small sample size. So what the student t distribution does is it adjusts for that by giving us a bigger value for that t. So let's plug everything in. We've got x bar minus t sub alpha over 2 times s over square root of n, and that should be less than our actual population mean, and then that should be less than x bar plus t sub alpha over 2 times s over square root of n. And we're going to plug in everything that we know. X bar, 122.9. Our t sub alpha over 2 that we just found on the chart was 2.306. Our S is 34.2. And our N, now don't use the 8 here. Here we do want the N, is 9. So square root of 9. And that should be less than the mean, should be less than the same thing on the other side, but with a plus. 2.306 times 34.2 over square root of 9. Now you're welcome to just work the whole left side straight through and get your answer, or the whole right side and through and get your answer, but I like to do just the part after the plus and minus sign and get my margin of error. Okay, so slide this over so we can see better. Go. All right, so we have 2.306 times 34.2 divided by square root of 9. Or if you know square root of 9 is 3, you could just put in 3. I'll go ahead and do square root 9. Enter. Now you only need the same number of decimals that your mean is rounded to. So since we have 122.9, we only need our margin of error to go out to the same amount. So 122.9 minus 26.3, because it's 0.28, so we'll say 26.3. So 26.3. Now I don't have to recompute that on the other side because it's the same computation. So on the other side it's just going to be 122.9 plus 26.3. So when I take 122.9 and I subtract the 26.3, I'm going to get 96.6. So my lower bound for my confidence interval is 96.6. And then when I do my upper bound, I would put in 122.9 plus 26.3, and I would get 149.7. So that's our confidence interval. We are 95% confident that the actual average age, the actual mean age of these Galapagos tortoises is between 96.6 years and 149.7 years. Hold on. There's a discrepancy from the slide to what I just computed. Let me double check and make sure I didn't put something into the calculator wrong. Oh, I see what's happened. The problem has a wrong number here. So what we wrote off to the side here is correct. This was computed with 34.9 as the standard deviation, and that's not correct. So this should have been 34.2. That was what was in the problem. This should have been 34.2, which would have given 26.3. So that means our number on the right side here isn't correct. Let's fix that. Okay, so this would be 122.9 plus 26.3, because I was just looking at the answer before. So it's 149.2, not 149.7. Okay, we'll cross that off here too. So it should be 96.6 to 149.2. And so we are 95% confident that the actual average age, mean age of the tortoises is between 96.6 and 149.2 years. Now you notice that's a pretty wide gap between 96 years and 149 years. It's, well, it's over 50 years. And so you say, well, is that useful? Yes, it's as useful as we can get for this situation. We only had a sample size of 9. That's a really small sample size. And that is possible when you have, small populations of things like the Galapagos tortoises, where they're either, it's a small population, so you can't take too much for your sample, or they're difficult to collect, those types of things, are difficult to figure out. I mean, how do you know how long a Galapagos tortoise lives? So it's difficult to collect, so you end up with a small sample. But it is a pretty wide range because we had only a sample size of n, and because we wanted to be 95% confident, we get a pretty wide confidence interval. All right, so that's it for section 7.3. And again, I'm going to go back and I want to apologize. We've got a mistake on the slide. This should be 34.2 like we wrote it over here on the side. And then this should be, everything else should be the same, but then the answer comes out to be a margin of error of 26.3. Add that and subtract it, and that gets us 96.6 and 149.2. Okay, so make sure you have that in your notes correctly, and I apologize for that error. All right, so now the last thing that we need to do in Chapter 7 is we need to look at our final type of confidence interval. And our final type of confidence interval is for proportions. And we're also going to do the sample size that we did with Section 7.2 when we had a certain margin of error we wanted to maintain, and so we would determine what sample size we needed for that. There will also be that for proportion. You can't do that in Section 7.3 because you need when you're doing means, you need the population standard deviation. So that doesn't work in 7.3 where we don't have the population standard deviation. All right, so this is Section 7.4. This is the last section for Chapter 7. And we're going to be doing the confidence interval for a proportion. And we're also going to be determining a minimum sample size if we want to keep our margin of error at a certain level. So I know I promised you that you would get tired of this slide, but I'm going to go back to this slide again. And we're going to look at where we're at on Section 7.4. So in Section 7.1, we had means where we knew the sigma, and so we used z. Not 7.1, but 7.2. That was in Section 7.2. In Section 7.3 that we just completed, we had that we were doing means, but we only had the s, and so we used t, and that degrees of freedom. Okay, so we had to figure out the degrees of freedom, and we had to stop at that level on our chart instead of going to the bottom. But now with proportions, proportions aren't reliant on a standard deviation, so we don't have to worry about whether we have the standard deviation or not, and we can just go back to using z again. So in Section 7.4, we're going to use z again. So what is a proportion? We've talked about proportions, but just a reminder, if you say something like 10% of all people are left-handed, 0.03 of people have green eyes, 2 out of every 5 adults went to college. These are examples of proportions. It's how much out of the whole. You can do it as a percent, a decimal, a fraction, but instead of being the average of something, it's how much out of the whole meets that criteria that you're looking at. So if X people in a sample size have a characteristic of interest, like green eyes or left-handed, then the sample proportion, which is P with a little upside down V on top of it, it's pronounced P hat. And in order to find P hat, we just take how many people in the sample have that characteristic out of the total sample. Kind of similar to what we did with the P and the Q when we were talking about probability. So our P hat is just how many out of our sample have the characteristic out of n in our sample. And then to get our Q hat, we just take 1 minus P hat. And that will get us our Q hat. So, in other words, P hat plus Q hat should equal 1 or 100%. That should be everything, because you're either in the, you either have the characteristic of interest or you don't. So it's like a binomial situation. So let's calculate a P hat and a Q hat with an example. So let's say we have a survey of 80 households and 17 of them had a landline phone. Well, we know that N is 80 and X is 17. So to calculate P hat, we're just going to take 17 out of our 80, and that's going to calculate our P hat. And that is 0.2125 or 21.25%. In the formula, you're going to be using the decimal or a fraction. You can also use a fraction, but you don't want to use a percent in your formula. And then the Q hat is going to be the rest of it. Now, you could say, oh, that's 63 out of 80, but I think it's easier to just take 1 minus 0.2125 or 100 minus 21.25, whatever way you're more comfortable with. And that would get you 0.7875. So we're saying if 21.25% had a landline, then 78.75% don't. Sorry, I wrote that wrong. Just a second, I confused myself. Take that off. All right, so 0.7875 or 78.75%. So 78.75% of the households did not have landlines, 21.25% did. That's our P hat and our Q hat. And just as a reminder, P is the population proportion. So P is population proportion. And then P hat is our sample proportion. Now this is a little bit different because we don't have a Greek letter like we do for some. So the way I remember this one is P is the big old population, and then the P hat is just the little sample. And I think of it as like a little guy with a little hat. So the little P hat, little guy with the little hat, his little baseball cap on, he's just the little sample. So you have your population, and then you have P hat, and I'm just a little sample with my little hat on. I know it's silly, but if it helps you remember it, that's okay. So here's our formula. Just as before we used a point estimate for the population mean, we can do a point estimate. So we could say, like in that last example, that, well, because we got 21.25%, we'll just assume the population is 21.25% of the population have landlines. That's probably not right. That's oversimplifying things from a fairly small sample. So it would be better if we could build a confidence interval. The margin of error is this value right here, which isn't really going to be as important as the whole formula. So our whole formula for doing confidence intervals for proportions is this formula. Looks kind of similar to what we had before. We have a number in the front, we have a minus. On the other side we have the same number, the P hat with a plus. We're still going to have our z sub alpha over 2. And then we still have a square root of n, but this part here has everything within inside the square root. We don't just square root the n, we square root everything. And on top, we're going to have P hat times Q hat. And then in the middle, instead of having mean, instead of having mu, we're going to have P, because we're trying to figure out a lower and an upper boundary for our estimate of the population proportion. As always, it'll be easier once we do one to understand what we're doing. Now remember again from our slide that we're going to be going back to using z, and you can even see it, you can see it in the formula. The formula says we're just going to use z now. So we don't have to stop at our degrees of freedom. We can just go all the way to the bottom of the chart and grab our z's. All right, so confidence interval for proportion will look like this. Using the survey that we had, 80 households found that 17 of them had a landline phone installed. Find a 99% confidence interval. Well, we did p hat as 17 out of 80. If we hadn't already done this, we would have to do this, which was our 0.2125. And then we use that to calculate our q hat as 0.7875. And then besides that, we need our n. We already know n, that was the 80 that we used up to find the p hat. So n is 80. What else do we need? We have p hat, we have p hat q hat, we have n. Oh, we need our z. So our z is 99% is what we're going to use. So let's go to our chart and see what z value we get for 99%. Get rid of what I've got on here. All right, so we're going to go to the top and we're going to make sure we're in the 99% column. And we're going to go down. Since we're doing z, we can go all the way to the bottom. All the way to the bottom. And remember, the z's are in the last row. So we come over and we find that our z is, we're going to round that to 2.58 because that's what Alex always does, so we don't want to get our homework answers wrong. So 2.58 is our z. And now we're ready to plug everything into the formula. So using this formula, p hat is 0.2125. Our z sub alpha over 2 is 2.58. Our p hat and q hat are 0.2125 times 0.7875, and then that's going to be over 80. And that's going to be less than our proportion, than our sample proportion. And we do the same thing on this side, but with a plus sign. So plus 2.58, and then our same things under our square root, 0.2125 times 0.7875 over 80. Okay, so clear this out. We've got, I sometimes will work what's underneath the square root first and then just multiply it by 2.58, but I think I'll just go straight for it this time. So 2.58 times square root of 0.2125 times 0.7875 divided by 80. Now, be really careful with your calculator. My calculator will keep that all underneath the square root bar. Some calculators you have to make sure you put parentheses or something so that it knows to keep that under, but make sure all those numbers are underneath. In this case, it doesn't matter that we're not putting parentheses around the top because order of operations would do that anyway, but you could also put a parentheses here in front of the 0.2125 and end it after the 0.7875 to show that this part is on top, but it's not necessary in this case. Okay, so what does that give us? That gives us 0.1179. So we're going to need to round that to 118. So 0.2125 minus 0.1180. Because we want that 79 to round up, and in order to round that up, we're rounding to this 9, this where the 9 is, the first 9, so 1179, but that 9 has another 9 after it, so we want to round that up. So the 79 becomes 80. And then on the other side we'll have the same thing, P in the middle because we're doing proportion, and on the other side we'll have 2125 plus 0.1180. And again, it's fine if you want to, try to put it in all at once. If that works better for you, you can just jump from here to the final answer. I find I make less mistakes when I do it this way. 0.2125 minus 0.1180 gives me 0.095 on the left side. And then on the right side, if I take and add 0.2125 to 0.1180, I get 0.3305. Again, a pretty wide margin because we have a pretty, for proportions, 80 is a pretty small sample size. Proportions, you tend to need a lot bigger sample sizes. And so 80 is pretty small for a proportion. So we're 90, and we're also trying to be 99% confident, remember. We are using a 99% confidence interval. So in order to be very confident, we end up with a pretty wide interval. So somewhere between 9.45% and 33.05% of households have landline phones. We can say 99% confidence that between 9.45% and 33.05% of all households have landline phones. Again, pretty far apart, roughly about 10% to 30%. That's a pretty wide gap for trying to estimate something. But we are 99% confident it's in there somewhere. Okay, so the last thing that we have to do in section 7.4 is to work with, what do we do if we have a researcher and before they start their research, they know that they want to stay within a certain margin of error. So if we take that formula that we had for margin of error and we solve it, we get this formula. This formula is on your sheet. You don't have to memorize it. You point it out. So on your sheet, it'll be on the first page. And it is right here. So to get your sample size in, you're going to use this formula. You don't have to memorize it. You just have to know that when they're asking this question, this is what they're asking for, and you need to plug into that formula. So if we have a good approximation of p-hat, like perhaps there was a prior study, remember we haven't done the study yet when we're trying to decide what sample size we need for our study. We haven't done the study yet. We're trying to do it, we're trying to figure out our sample size before we do the study. So we won't know p-hat. And so maybe from a prior study you have an idea of what p-hat might be. You could use that. If you don't have that, then what they do is, if we don't know p-hat, then we say p-hat and q-hat are 0.5. And the reason that we do that is we want to err on the side of caution, so make our sample size as big as could possibly be needed. And when you take two numbers and multiply them, two decimal numbers between 0 and 1 and multiply them, we actually have kind of an inflection point here. If p-hat is 0.1, that means q-hat is 0.9, and we get 0.09. If we have p-hat is 0.2 and q-hat's 0.8, we get 0.16, and you can see how that progresses. Then we come up to 0.5 and 0.5, we get 0.25. Well, that's bigger than any of the ones we had so far, but Once we go to the other side of that, then we start repeating things. So 0.6 and 0.4 is the same as what we had for 0.4 and 0.6. And so it starts repeating itself, so instead of going consistently upward, it's now going consistently downward. So this is the biggest value you can get from a p-hat and a q-hat. So we err on the side of caution. So if in your homework problems, I won't do this to you on the test. On the test, I'll give you a p-hat. But if on the homework they don't give you a p-hat, then you could just use p-hat of 0.5 and q-hat of 0.5. So let's solve one of these problems. This will be our last example for chapter 7. So we previously constructed this 99% confidence interval for the population with phones. Our sample size was 80, and remember, we had a pretty wide confidence interval. So let's say the researcher doesn't like that. They're going to do another study. How large a sample would we need if we want a margin of error at most of 5%? Okay, so we had a margin of error, remember, go back up here. Our margin of error here was 11.89 was our margin of error. So they're saying this researcher would like to do it so we have at most 5%. What would we need to do? So let's fill in what we know. So first of all, you have to really watch for this question. It's not saying construct a confidence interval. It's asking how large a sample. It's asking what is Rn? How large of a sample do we need? So that's this formula, not the one for confidence interval. We're going to be using this formula. Okay. So what's our p-hat? Well, our p-hat, we're going to just use what we got on the prior sample. So we're going to use 0.2125. And then we're going to use q-hat as 0.7875. And this will change for every problem. We're using the same ones, just kind of make our life easy for these examples, but of course in your homework they'll change. We already know from our prior example that at 99%, z sub alpha over 2 is 2.58. We'd have to relook that up if we hadn't just gotten it from the prior example. And then our E. So our E was given as 5%. But when we do calculations with percentages, we always change that to the equivalent decimal. So instead of 5%, we're going to use 0.05. So we want to know what N is. We're going to plug in p-hat and q-hat and z sub alpha over 2 and E into this formula, and that will tell us how large of a sample the researcher would need to make sure we stay with a margin of error of 5%, no more than minus 0.05, and plus 0.05. So N is equal to p-hat times q-hat, so in this case 0.2125 times 0.7875. Then we're going to multiply that times the z sub alpha over 2 divided by the margin of error, so 2.58 divided by 0.05. Now you can imagine one of the most common mistakes is just putting a 5 in there. Don't put a 5. That's 5%. We have to switch that to that decimal. And then we're going to square it. Don't forget the square that's up here. So if we calculate this out, it should come out to be about 445.6. Double check it. Don't want any errors that we don't catch. Okay, so 0.2125 times 0.7875 times parentheses 2.58 divided by 0.05 parentheses, and then we can put our square on there. Can you either use this up arrow that I just used? So I use the up arrow and then I put a 2, or you can just use the square button. They both should work. And so that comes out to be approximately 445.6. Now, remember with these that that's the minimum sample size. So we can't go down in our sample size to 445. We've always got to round it up. So our N is actually going to be 446. The researcher would want to get 446 households sampled in order to keep that margin of error within that 5% that they would like to keep it within. All right, so one last thing before we go. I have 2 slides with these flow charts on them. One to finalize Chapter 7 and one to give us a lead into Chapter 8. So stick around for 30 more seconds, okay? So you know that we've been looking at this as far as our confidence intervals. And when we were doing confidence intervals for a mean, we had to decide, do we know the sigma or do we only know the S? Sigma led us to using Z and S led us to using T. And then if we had a proportion, then we knew, and the T meant we had to use degrees of freedom. Okay? And then we know now that if we have a proportion, we can always just use Z. We don't have to worry about it because standard deviation doesn't come into play with proportions. But I have a slide for our next chapter. So our next chapter, we're going to be doing hypotheses test. So we're going to be doing a hypothesis test for either a mean or a proportion. And one thing that you'll like is that once you get this kind of pattern figured out from Chapter 7, we use the same pattern in Chapter 8. So even though you don't know what a hypothesis test is yet, we still are going to ask the same question when we do a hypothesis test. We're going to ask, is it a mean or is it a proportion? If it's a mean, we need to know, do we have the sigma or do we only have the S? If we only have the sigma, we're going to use Z. If we only have the S, we're going to use T with degrees of freedom. And then if we have a proportion, we can go back to using just the Z. And to make it even more kind of relatable, this in our next chapter will be section 8.2. Remember that was when we were doing confidence intervals, that was 7.2. When we're using T, that'll be section 8.3. And when we're doing proportion, that'll be section 8.4. So they match up in the section numbers just with the different chapters, 7 or 8. But that'll be a familiar pattern that we'll see again in Chapter 8, and it'll be very important that you can recognize that so you know which one of those to do, which formula to use when you go to do your hypothesis test, just like you needed to know when you're doing your confidence intervals. So I will see you back for Chapter 8, and good luck with your Chapter 7 homework.